Jairam ki, we'll discuss instrumentation in food analysis. We have already seen that in macro analysis, we do it at percentage level. But for micro analysis, there are constituents, components, which we do it at ppm, ppb or ppt levels. So for such low levels, low detection limit, low quantification limit, organics as well as inorganics, compounds like residues, contaminants, adulterants, nutrients, mycotoxins, we need to do it by instrumentation. So need for food analysis, one, characterization, fine. We have known that protein, amino acid, they are all large quantity, sugar, dietary fiber, they are all characterization techniques which are normal chemical wet analysis, etc. But for instrumentation, constituents like nutrients, vitamins, minerals, additives which are added in very small quantity, colors, dyes, stabilizers, antioxidants, highly toxic, non-toxic constituents, we need instrumentation. Contaminants, intoxicants of what type? For example, biological, microbes and pathogens and mycotoxins. Chemicals, mycotoxin is one which is of biological origin. Residue pesticides, antibiotics, veterinary drugs, environmental pollutants like polycyclic aromatic hydrocarbons, polychlorinated biphenyls and dioxin, toxic metals like lead, mercury, arsenic. So for all these kind of trace elements, trace components, we need instruments. When we need instrument, we must understand which instrument is better. We check for certain criteria for an instrument. The first and foremost criteria is repeatability. What do we mean by repeatability? If same operator, same sample, same equipment and same method, if the person is doing multiple times in the same laboratory, in the same place, what is the result he is obtaining? If the result is same, that means repeatability is very high. What does it mean? We means repeatability is same as standard deviation. Okay. So we are looking for an equipment which gives same result all the time if done in same laboratory. Then there is a term, the equipment has to have very high precision. What do we mean by precision? We compare different observed values. We have seen in the repeatability experiment, several values were obtained. So we compare those values. First, we determine the average of those values. Suppose an analyst has got 100 values. Determine for the same sample, same equipment, same lab, same condition, same method. If he has done and got 100 observations, so for precision, we take the average of it. Then we calculate standard deviation, how each value deviates from the average. Now that is all these deviations we add together and we get the absolute deviation. That absolute deviation we divide by the number of values for getting the precision. I'll repeat it once. We have 100 values, for example. All those values, we make an average of it. 100 values, what is the average of it? From the average, we find out each value, how it is different, deviation for each value. Those deviation we add together. So we have the absolute deviation. That absolute deviation we divide by the number of observations to get the precision. We are looking for highly precision equipment. So repeatability and precision, to differentiate, I just thought it is better to explain, determines trust of measurement repeatability. And precision will tell us how much results differ from each other. Test sample many times with the same tool is repeatability, whereas in the case of precision, measure multiple parts with different testers and tools and find out the absolute deviation to calculate the precision. It sets the limit for level of precision in both the cases. It determines variation expected from any measurement process, repeatability. In the case of precision, it's variation between different parts produced by same process. Repeatability is important for the person who is taking the measurements. Precision is important for the person who is designing the product. So say, for example, if 5 different measurements have minimum variation or same value, then the designer will think the process is repeatable. So you can understand the equipment should be high repeatability, high precision. but it should also have high accuracy. Then there is a term called reproducibility. Same sample, but different laboratory, different person, the same method in different places. So a measure of ability to reproduce result using same experimental approach in same as well as different laboratories using same as well as different equipment. Repeatability, same lab, same equipment, everything is same. In the case of reproducibility, all are the same, but the laboratories can be different. The person who is doing also can be different, which was not the case in repeatability. So criteria of selection of equipment is, number one, it should give the value very close to the true value. It should be accurate. The first is how close the measured value is to true value. That is accuracy of the equipment. Then it has to be very simple to use. Even the unskilled worker can use it. The speed, how fast it is able to analyze, throughput of the analysis. Sensitivity, that is lowest limit of the detection. A particular analyte which the equipment is able to go lowest level for quantification as well as detection is sensitivity. And then it is able to specify, for example, in a mixture of fructose in a mixture of sucrose and glucose, if you want to specifically determine fructose, that is specificity. So various constituents of similar nature, if you are specifically identify one which you are looking for, that is specificity. These are the criteria for instrument selection. Now let us talk about techniques, instrumental techniques. So we take first technique, chromatographic technique. To understand this technique, we must understand what is chromatography. Please understand, chromatography is nothing but the separation when the material is migrating. It is dynamic differential migration. How does it happen? There are two phases. One is solid phase, the other is either liquid or gas. So there are basically two phases through which the material or with which the material of interest is in contact. So the constituents will be moving continuously, okay, in a given direction, and the constituents will be in touch with one phase which is solid always, and the other phase either liquid or gas. So basically the components are moving along with the mobile phase. So there is mobile phase which is moving, taking all the constituents together in the instrument, and there is a stationary phase which is non-moving. It remains stationary. So the mobile phase is carrying all the components together in the mixture along with it. Now while the material is moving, there is a dynamic differential migration. What does it mean? While the movement is happening, the components are in equilibrium with one mobile phase and the other stationary phase. Now if the material likes more mobile phase, it will go ahead, move. But if a component likes the stationary phase, it will attach with the stationary phase and it will move slowly. So that is dynamic differential migration. So what actually happens is, analyte exhibit different mobilities due to differences in either adsorption property or partitioning or solubility or vapor pressure, molecular size or ionic charge. For example, the mixture of sample in the mobile phase is moving continuously in a direction over the solid phase. If it is a very high adsorption on the solid surface, it will move slowly. So at the end of the column, it will reach the slowest. Whereas a material which does not adsorb, would like to remain with the mobile phase, will move with the mobile phase. So this is the way we separate different components. This is chromatographic technique. Now if the mobile phase is liquid, it becomes liquid chromatography. If the mobile phase is gas, it becomes gas chromatography. The stationary phase in all cases is always solid. Let us see the partitioning because of the separation because of the adsorption. We call it as adsorption chromatography. Here, as I told you, a solid stationary phase, and the mobile phase can be liquid or can be gas. Now, the mobile phase is carrying all the constituents, mixture of constituents, which we are analyzing. So different solutes travel differently through the solid, And the competition is between the adsorption and solubility, because in the mobile phase they are dissolved, all the components. If they adsorb more on the solids, they will become slow. So the least soluble, which will, that means most adsorbing or best adsorb, will travel the slowest, and separation into bands of different solutes. The ones which are most soluble will be very fast moving through the column. This is adsorption chromatography. Let's see partition chromatography. Here the equilibrium is driven by solubility. So suppose if the components are with the stationary phase, which is a non-volatile liquid, is, for example, more affinity for that, we generally these kind of this partition chromatography is done with the stationary phase. There is a non-volatile liquid layer on the top. Now that non-volatile liquid layer will have a affinity for the components. So if components are more soluble in that non-volatile liquid layer, they will stay there, they will move slowest. If they are more soluble in the mobile phase, they will move fast. So more soluble in mobile phase reach the end of the column first, and the solutes will distribute accordingly. Paper chromatography is the example of partition chromatography. We are talking about equilibrium that the component or constituents of the sample are maintaining between the stationary phase and the mobile phase. In the case of ion exchange chromatography, the state of equilibrium is between the ions. It is similar to partition chromatography, but there it was because of solubility. Here it is because of the exchange of ions, because there is a resin on the stationary phase, and resins will have counter ions which will exchange with the sample. So when the liquid mobile phase elutes through resin ions, bound ions will get released, and the other ions are bonded preferentially. So they will go slowly, those which bind with the resin, and those which do not bind with the resin will move fast. The ion exchange reagents are generally used for domestic water softeners. The hard water is softened by ion exchange reagents. Then there is molecular exclusion chromatography. Please note that in the case of molecular exclusion chromatography, there is nothing called equilibrium. There is no equilibrium that exists between components, constituents, and the two phases. Here what is done in molecular exclusion chromatography is that the components, the mixture, passes as a gas or as a liquid through a porous gel. The gel is designed in such a way that the bigger particles will move unhindered, uninhibited. They will move fast. They will go without passing it through the gel. The smaller particles, however, has to permeate through the gel, and because they are permeating through the gel and the gel size is such, they slow down. The smaller the particles in the mixture, the longer they will take to get to the end of the column, and the separation is according to the particle size. This is basically done for the molecular polymer compounds, where molecular weight of different sizes are there. When they pass through the gel, as the molecular weight particle size is going through, the different molecular weights will separate at different rates. Now let us take one by one. Gas chromatography we will take. We have talked about the chromatography basics. We'll talk about the instruments now. Now this is gas chromatograph we are talking. So in the gas chromatograph, the mobile phase is gas. The stationary phase is generally solid or liquid. Now small inert particles like diatomaceous are coated with liquid, okay, providing large surface area for the solute to equilibrate with gas solid chromatography it will become. But if the stationary phase has a liquid layer on it, then it will be a gas liquid partition. The stationary phase particles are coated onto they are in the column, the stationary phase that we have just talked. The gas is the mobile phase. The stationary phase can be solid or liquid. If it is liquid, that also is supported on the solid. But all of this is existing in the column. So the material which is under analysis will pass through the column in contact with the stationary phase and passing it along with the mobile phase. Let us see the key features of gas chromatograph. We inject the sample through a self-sealing disc, normally we call it as rubber septum, into a small heated chamber so that it gets into gas form. Remember, in gas chromatography, the material is supposed to be in the gas form. That's why it is gas chromatograph. It must go into the column as a gas. It should not be in the form of a liquid. So it should go in the gas, so should remain in the form of gas till it comes out. The injector oven is about 50 to 100 centigrade hotter than the start of the column, so that the material remains in the gas form. And the mobile phase is generally the helium or nitrogen. And the gas that we are using as a mobile phase must be dry. So all the organic impurities must be removed by passing it through the activated charcoal. All gas chromatography equipment are designed in such a way that only the dry gas gets into the chromatograph. The column is coiled to fit into the thermostatically controlled oven because it's a small equipment. So columns are all coiled. They can be either packed or they can be capillary columns. The temperature of the oven is kept constant for good separation. But in case if the compounds are not getting into gas form easily, then maybe we increase the column temperature. But the increase of column temperature can be programmed in order to have better separation. So it is done all computer controlled. So we give a program and we change the temperature, increase in temperature gradually with a program to make sure that the separation is fast. Once they separate, we find out from the injection till the end of the column how much time the component has taken. So that is called retention time. So retention time becomes the basis to identify components which have separated. For example, we take a known compound, we inject the compound and find out how much retention time it has given. How much time from the injection? We inject the sample and after the column it is separated and we see it at the detector as it reaches to the detector. That time, how much time it has taken will be its retention time. A known compound, once we know it is the retention time, then every time we analyze samples and if that retention time is there, then we will say in the mixture this particular compound is present. But remember, it can be misleading because just by one experiment of knowing retention time is not good enough. We must have the fundamental concept of retention time, which is not fixed. It depends on number one, flow rate of the carrier. At what flow rate the gas is moving, the mobile phase is moving. What is the temperature of the column? We have just seen, in case if separation is slow, maybe we increase gradually the temperature. What is the length and diameter of the column? What type of column we are using? What is the nature and interaction of solute with both the phases? The nature of interaction of the solute with the different phases, this stationary and mobile, and the volatility of the solute. So these are the factors. So before using the retention time, we must make sure that all these factors are taken into account. Now remember, in the case of, we already know we are doing microanalysis. The constituent that we are going to analyze is in very, very trace amount. So many a time we are not able to have the low quantification, LOQ and LOD of the equipment. We can't go low. So what do is we have certain sampling techniques. The most common sampling technique these days is headspace technique. What is headspace? Headspace is the sample which we have prepared. We take it in a sealed vial. So in a vial, sealed vial, we put the sample and we equilibrate it at fixed temperatures, say for example 100 degrees or 120 degrees, depending on what sample we are doing it. We equilibrate it at a fixed temperature. The purpose is that the constituents which are there in the liquid should come up in the vapor form. So if it is, maybe it is 50 degrees, maybe it is 60 degrees, depending on what constituent we are talking of. So for example, for 10 minutes, we equilibrate it, the constituent will come in the vapor form. It will be more concentrated in the vapor form rather than in the solution. And that vapor we inject in the GC. So by this, we try to achieve lower liquefied LOQ, limit of quantification, and low limit of detection. The other sampling technique is thermal desorption. Suppose we have solids So solid sample or semi-solid sample. So like we did it in the head space, we put the sample, okay, in the vial, and we heat it and make the inert gas flow over it. Okay. So when we are heating it, the volatile components will come up. The air will lift the volatile components, organic compound. We extract them from the sample matrix into the gas stream, and that gas stream we put it into the inject into the GC. So it is generally used for the. It is not supposed to be for the wet samples. The sample should be dry. Sample should be uniform, and it is generally done for, like for example, volatile organic compounds in wine, or beer, or alcoholic drinks, volatile organic compounds. So, or it is done, for example, we want to find out flavor profile of coffee, okay, or we want to find out volatiles in compounds, in various compounds, solid compounds, like honey, we want to find out volatile compounds. Mushroom, we want to find out volatile compounds. So in that case, what we do is we take the sample, we heat it. At the same time when it is heated, the flavors and odors will come up, pass the inert gas over it, and that gas we inject to the GC. Then there is another technique which is purge and trap technique. Now it's sort of a thermal desorption technique, because here we are going to dissolve the volatiles. How do we do it? We purge the volatiles in the liquid sample. Again, like in the head space, the liquid sample is in the vessel, and we purge it with bubbling air or nitrogen. It is preferred to do it with nitrogen. Collect the volatiles in the tube containing a suitable sorbent. So basically, first what we do is we purge and then we trap. Once it is trapped, then that sorbent we heat, and we dissolve the substance which is trapped. So that's why it is called purge and trap technique. So after desorption, the volatile will be released, and we then inject it into GC. Now what this method is for? It is suitable for non-homogeneous samples. Okay. For example, large and high moisture samples like pizza or fruits, the measurements of mal order in organ and due to organic volatiles, and various kinds of, in order to find out whether the food is fresh or not, because the fresh fruit will have different order. The fruit which is kept, which has lost its vitality, it will have a different order. So this is the technique which is used for the sampling technique for checking the freshness of the food product. Let us talk about the detectors. We have seen the column through which the mobile phase will pass. The products will be separated. After they are separated, they are supposed to be detected. So the very popular column is thermal conductivity detector. What does it do is, it checks the response, okay? It checks the conductivity difference between carrier gas and vapor of the analyte, okay? So the carrier gas along with the constituent which is in the vapor form, what is the difference in their thermal conductivity is checked by the thermal conductivity detector. What it consists of? It consists of two pair of heated elements, okay? Each has an arm of the Wheatstone bridge. We know in Wheatstone bridge, we have 2 and 2, four arms are there. So in one stream, the mobile phase will pass. In the other stream, the mobile phase with constituents, the sample will pass. So the reference gas, that is a mobile phase, if there is no constituent, then the Wheatstone bridge is balanced. The conductivity in the Wheatstone bridge is balanced. But when the analyte reaches the filament, I mean, till only mobile phase is going, it is balanced. The moment the analyte reaches the filament from the column, the thermal conductivity is changed, because there is a difference in thermal conductivity of mobile phase and the product. So that change is recorded by the thermal conductivity detector. So TCD detects changes in thermal conductivity of the gas. Generally, it is tungsten rhenium filament, and it must be kept at a temperature so that solutes are in the gas phase. In all throughout the column, the detector, the sample should be in the gas phase, which means the temperature of the detector, of the column, of the injector should be in such a way that the material is always in the gas form. The other detector which is very popular is flame ionization detector. What do we do here is all the gases which are from the sample, after the column they come out, we burn them in with hydrogen and air. Okay, when we burn them, then they get oxidized. Okay, so the CH radical, okay, is combustion makes the aldehyde ions, and these ions will obviously transmit current, and we record the current. Okay, as a the signal current will be the one which will be recorded at the chart, and we'll get a chromatogram. Okay, now the point here is, may not be all the radicals will be converted into ions. There might be 5 out of 100 which will form into ions, but the fact is the proportion will always be constant. Each time it will be 5 out of 100, 10 out of 100, because the proportion is constant, and this is the proportion is the one which is going to tell us how much is the content of that product. So this there is no problem, because the signal will depend on the content. If the proportion is constant, the signal will also be constant each time. The flame ionization detector is 1000 times more sensitive than thermal conductivity detector. But remember, the principle of flame ionization detector is that the material, the gases which are coming from column must burn first. And after they burn, they also produce ions. So these compounds which are not able to do that, this detector is not good enough. Nitrogen phosphorus detector, which we say NPD detector, does the same thing like the ions formed in the FID. In FID, gases are burnt and ions produced are done there. Here, what we are doing is, it is more for the nitrogen and phosphorus. So gases of the column are forced through a jet, okay, in presence of air and hydrogen, to pass over the surface, which is very hot, okay. It's basically rubidium salt. So it is very hot, hot salt in the form of a bead, okay, bead. So excited rubidium atoms, they ionize nitrogen and phosphorus. Remember, it is same as FID. In FID, the gases are burnt and the aldehyde ions are produced, or carbon ions are produced. In this case, it is only nitrogen and phosphorus. So this detector is specific to nitrogen and phosphorus. Now, why it is so important? It is important for compounds which are organophosphorus organic compounds and nitrogenous compounds. Say, for example, the carbamates, for example, pesticides, or organophosphorus pesticides like malathion, parathion, dimethoate. So these are the pesticides. For their residues, always in the GC we use NPD detector. After gas chromatography, let us talk about liquid chromatography. Here the equilibrium is due to adsorption and polarity. Adsorption is driven by polarity. So we use a column containing silica gel or alumina. Okay, it is perfect example of adsorption chromatography. The solvent put into the column is called eluent, and the material that flows out of the column at the end of the column is called eluate. So eluent and eluate. Eluate is the one which is actually detected at the detector. So we have already seen that liquid is the mobile phase. Inert solids such as silica and alumina are the stationary phase. Silica and alumina have different nature. Silica is acidic, so obviously it will absorb the basic compounds, basic components. Alumina is basic, so obviously it will have more affinity for acidic components. So when we are having components in the food which are acidic or basic, the gas chromatography will not be the ideal thing. The ideal thing will be liquid chromatography, because there we have in the column the silica gel and alumina. We can also use magnesia. And remember, these columns, these stationary phase is sensitive to water. So if it has absorbed water, then its sensitivity will be affected adversely. But the good thing is this adsorption can be the absorbed water or adsorbed water is reversible. So suppose if the stationary phase has absorbed water, the column can be recovered by heating it, removing it moisture, putting it in the oven for 24 hours. All the moisture will go and your column is ready for fresh samples. Then there is thin layer chromatography. I think this is something which we also call it as students in the schools when they are taught about chromatography. This is the best example. What do we do is the stationary phase remains on the glass plate, okay, on the layer of alumina or silica of smaller particle size, okay. The stationary phase is a thin layer of alumina or silica of smaller size supported on a glass plate or aluminum foil. So how do we do it? We make the slurry of alumina or silica, we make a small layer on it, and then that becomes the stationary phase. Now suppose on the glass we have taken the layer of alumina or silica. We at one end of the plate we put the sample, okay. So and that we dip it in the solvent. So we take the solvent and put the plate, you put it in the solvent, and the solvent should be at the point where the sample is, okay. Solvent will obviously rise, but the dipping of the plate is in such a way that the solvent touches the point where we have put the sample. So you would see, and you must have seen it many times in the lab when we do the experiment for synthesis, etc. We want to find out how the reaction is going on. The best way is to pick up the sample, put it on the thin plate, which we have made the stationary phase, and do it by TLC. Well, how many components are there? Because the solvent will start moving up with the capillary force. And as it moves up, there is a partitioning of constituents. So you will see different spots in the layer at different places. So that is how we do the thin layer chromatography. What is the separation efficiency? We should talk about it. It increases with reduction of particle size in the stationary phase. In the liquid chromatograph, remember, the particle size of the stationary phase plays a very big role. So for example, porous silica, particle size is 10 raised to the power minus 6 meter. The surface pores is of the size of 10 raised to the power minus 8 to 10 raised to the power minus 9, nanometer scale. They are covalently bonded. Okay, so small particles means high capillary action. So in the column in LC chromatography, if you take in the column stationary phase of small particles, so very high capillary force. So if you are doing LC by gravity, like we used to do it in the schools and colleges experiments in the column, and we let the material move with gravity, it will be impossible to do the chromatographic experiments. So the stationary phase particles are packed into, they are supposed to be, the mobile phase is supposed to be pushed or with the pressure. So we apply the pressure, and that is when the technique becomes HPLC. Okay, the high pressure is applied, so the mobile phase moves faster. If we do not apply the high pressure, then we will have a very long separation, and that is not efficient. All equipment, liquid chromatography equipment now are HPLC. The separation in HPLC is so efficient that there is no need of long columns, because otherwise you will have to have a very long column to have fast separation. So we define the HPLC as high pressure liquid chromatography. Why high pressure? I have just explained to you that because the particle size in the column of the stationary phase is so small, nanometer scale, the capillary force is so high that with gravity or without pressure, the mobile phase will not move. If it will not move, how will we have separation? So high performance liquid chromatography will have actually 4 components. First is the solvent delivery system, which includes a pump. Okay, we have already talked about liquid chromatography. Having pump for mobile phase is the most essential thing. So it has a pump, it has single injection system. Okay, the pump is there to supply the mobile phase, injection system, column and detector, and chromatography software and computer. So basically these are the 4 components. After injection into the column, components of the sample separate due to differences. We have already talked about the dynamic differential migration, because differences can be because of the partition behavior, solubility, okay, between mobile phase and stationary phase. They pass through the column at different rates. The components which have more affinity for the stationary phase will come at the last in the column. Those which have less affinity for stationary phase will, like the mobile phase, they will move fast. Now the point here is what should be the mobile phase? Is it one solvent, more than one solvent? Depending on the analyte that we are doing it, we generally are the HPLC is done with more than one solvents. Now, if we have more than, suppose we have two solvents, we have two options. Either we have one composition of the solvents and do the complete chromatography with the same composition. That is called isocratic. So when the mobile phase has the constant composition of the constituents, like methanol water. Suppose my HPLC system is running the analysis with methanol water 50-50 throughout the experiment. Then it is constant composition and it is isocratic. But suppose if I am varying it gradually, 10% methanol, 20, 30, 40, 60, 80, then it becomes the gradient HPLC. And this is very important tool to actually separate components in HPLC by using the gradient mobile phase. Okay, two or more solvents of different polarities. Always we don't take the same polarity. The idea is we are trying to create a partitioning, okay, based on solubility, based on polarity of the components. The column of HPLC is about 10 to 30 centimeter long. It's not very long column, 4 mm dia. Long column should not be there. In fact, long column will need very high pressure. And we have already talked that in HPLC, we need to have high pressure. These days, in fact, ultra HPLC, HPLC are coming where the pressure is very high. Generally, the minimum pressure, the pressure pump is of 100 kg per centimeter square, 100 atmospheric, 10 megapascal. Now, that's a very high pressure. Now, for this kind of pressure, that means the robust pump should be there. Generally, the pumps which are used are twin cylinder reciprocating pump. So, they produce very high pressure. The flow rate are in the range of 0.5 to 5 centimeter cube per minute. Okay. The volume of the column are very small. I have already said that if the column is long, the requirement of pressure will be high. So we avoid it. Thus, the injection of sample must be very precise and quick. So the moment it comes out, it is the component is of very small volume, 5 to 20 mm meter cube. It's very small. The moment it comes out, it should be detected fast. What are the detectors of LC? The first is refractive index. Once the component has come to the detector, it measures the ability of components to bend or refract light. We know very well in the physical analysis, the general characteristics of food, characterization of food, refractive index is one of the parameter. It is nothing but the capacity of the component to bend the light. When the light moves from the solid phase to liquid phase, the light bends, refracts. So light proceeds through a bimodular flow cell to a photodetector. One channel of the flow cell directs the mobile phase passing through the column, while the other directs only the mobile phase. Okay. So there are two flow cells. One directs the mobile phase passing through the column, while the other directs only the mobile phase. The one which is passing through the mobile phase will have the components. So the difference in the refractive index of the one which is passing through the mobile phase and the one which is directly going into the flow cell will be the refractive index difference which is recorded. So detection occurs when light is refracted by components eluting from the column, read as a disparity between the two channels, and we get a chromatogram using the refractive index detector. We can use the ultraviolet detector, in which the ultraviolet of various wavelengths. We can have one fixed wavelength, lambda max, or we can have a range of it. diode, photodiode detector, which gives a three-dimensional graph, fluorescent detector, which checks the difference in the fluorescent properties of the component. Each component has a fluorescent property. They may vary from each other, but each one of them. What is fluorescent property of a component? Okay, it is nothing but once the light is absorbed, this substance re-emits it. And that is what is the fluorescence. And that principle is used for the fluorescent detector. Which equipment one should use, HPLC or GC? It depends on which industry we are talking about. Here we are talking about food industry. So in that we will have a look at what kind of samples we are going to analyze. So it depends on the industry. It depends on the chemistry of the compound. This comparison shows which compound should be better done by HPLC comparison to GC or vice versa. For example, if low volatile compounds we are doing, that means which are solid, semi-solid, which do not volatilize, HPLC is the best equipment. In GC, high volatile, flavors, odor, all components which are highly volatile. In HPLC, lipids and alcohols. In GC, residual solvents. In HPLC, amines and amino acids, antibiotics, mycotoxins and proteins, carbohydrate, sugar profiling. We can't do sugar profiling carbohydrates by GC. Only it is possible by HPLC. Organic acids and bases, the best done with HPLC. In GC, what is best done? Oils and fats. In fact, find out the fatty acid profile, trans fats, cholesterol. Okay, residual solvent GC is the best. So what we have learned from this session, we have learned about what detectors HPLC uses, what detectors are for GC. We have seen the difference between GC and HPLC. What is flame ionization detector, where the gas is burnt, it forms the ions which are detected. Electron capture detector, nitrogen phosphorus detector, thermal conductivity detector. Then detectors for HPLC are UV, refractive index detector, which check the Ri component difference, fluorescent detector. So these are the things which we have learned today. I hope you enjoyed it. Thank you very much.